Good morning, everyone. Let me start with today's topic. So till now, we have been talking about using CNN for the task of image classification. But there are other important computer vision tasks where CNN have been applied successfully with very good results. So we'll discuss them one by one. Probably in 3 classes, we'll need to discuss these different tasks. So a basic overview or summary of all those tasks are shown here. So one of the tasks is a segmentation task, which we already discussed earlier. In the context of machine learning based segmentation, we call it semantic segmentation. So the idea, as you know, is same. Each pixel level, we want to classify every pixel belonging to a particular class, basically. So a cat pixels belonging to a cat region will be classified as one class, and the grass region will be classified as another, and so on. So this is same as the segmentation task that we have seen earlier. So earlier we had seen more traditional vision techniques. Today we will see CNN-based architecture to do the same thing. The next task, which involves a localization, is another level of difficulty. So earlier we were just taking an image and classifying whether this image belongs to cat category or what. But now, if we can add one more thing to it, where we want to localize that particular object, or that particular class object that we have categorized this image to, and try to fit a bounding box around that object. So in that way, we are kind of localizing the area of that particular object category in that image. So we'll see how we can do that by modifying our traditional classifier architecture to do that thing. And then the next level of difficulty is object detection, because here now we given an image, not only we have to just give one label, we have to actually find multiple objects. So we have to find multiple objects in an image, be able to do a multi-classification basic kind of thing. So we should be able to classify multiple regions into a separate classes, and not only classify but also do this localization. So this classification plus localization task, instead of fixing it to just one object or one class in an image, now we have to do it for multiple objects in an image. So that becomes an object detection task. So here is an example. There are 2 dogs and cats, which are primary objects probably. So depending on what are the labels or what are the categories we are interested, we'll have to, if there are instances of those categories, we'll have to find them and find a bounding box around them. And then the last task that we'll discuss is called instance segmentation, which is a combination of object detection and semantic segmentation, basically. So in object segmentation, we are detecting objects, but we are just fitting a bounding box. And that bounding box, many times they overlap and they have a lot of background portions to it. But we may want to get a more accurate, we may want to have an exact segmentation. We want to segment out the object exactly, basically. So that involves combining this segmentation task and this object detection task. So the difference between object detection and instance segmentation is basically we are not just drawing a bounding box, but we are actually drawing the actual boundary or the contour of that object. And difference between instance segmentation and normal semantic segmentation is that in semantic segmentation, we don't distinguish between different instances of a class. If there are multiple cats here, we don't distinguish them as a separate class. We categorize them as single class. But here, if there are more than one dogs or more than one cat, we'll have to categorize. There are different instances of that same object class. We'll have to categorize them separately. So this is the way we will discuss them one by one. We'll first discuss this semantic segmentation, and today we'll also discuss classification plus localization. From next class onwards, we'll discuss object detection and instance segmentation. I hope we understand what is semantic segmentation. We want to basically group together similar pixels in an image, pixels which are semantically same, meaning they are belonging to the same region, same object class. We want to label each of those pixels with that particular category label. So for this image, we want to get this kind of a classification. So now instead of just classifying the entire image, we have to classify every pixel with a particular class. and this will be quite annotation intensive. To generate a ground data set for this type of image, we'll have to label each pixel now with a particular class rather than just labeling giving a single label to the entire image. Now we have to give a label to every pixel in the image, and there are tools available to do that. There are tools by which we can draw a polygon or form a contour around that things, and within that contour all the pixels will be given a single label and so on. So you don't have to manually give for each label. There are tools by which you can draw some shapes and figure bounding boxes or even contours around that in different regions, and automatically all the regions within that get a particular label. But it is going to be a little bit more manual intensive to do so ImageNet, for example, has millions of images in the dataset, but dataset for a semantic segmentation task can't have that much large dataset because the effort that will need is too much. It is too costly to do that. So, and of course, here in this task, we are not going to differentiate multiple instances. So if there are two cows, we may all categorize them just by a single label, because we are not making a distinction between multiple instances of a same class. So is that clear? So how can we use CNN to do this? So a very brute force idea or a naive approach will be to basically just take our normal classifier, our image classifier architecture, and just do a sliding window kind of a thing. Take a window, small window patch, that patch as an input to the classifier, image classifier, and that image classifier will predict that class looking into the content of that patch. So, for example, if you extract this patch, probably it will give it belongs to cow category. Then this patch will also belong to cow category. So the center label of that patch you label with that particular category, and this patch probably will be categorized as grass. So the center label you will be given as a grass. So in this way, you can categorize every pixel. But what is the problems with this approach? So the problem with this one will be, it's very simple, that it is going to be very inefficient. The main disadvantage with this is it's going to be too inefficient things. Taking out patch and running it through and passing it through the entire architecture and making a prediction. So what are all calculation we are going to do for this patch? Let us say we are going to extract features at each convolution layers and do all those operations. And when we take this patch, again we have to redo all those operations, although almost 90% of this patch and 90% of this patch is almost similar. So the same computation that we have done here, probably we'll have to repeat those computation, and so it's like it's very redundant. Basically, we are not reusing that computation. So ideally, we should be able to. So because when we pass this entire image to this architecture, we automatically calculate all the features at different levels for this entire image. So we should be able to do it we should do it just once. We should not do it multiple times and reuse that whatever features have been calculated for each locations. We should be able to reuse them instead of calculating them again and again. So that is the main disadvantage with this approach. Of course, accuracy point of view, as some people may have guessed, may not be so good, because for making a prediction of one pixel, we are taking a patch around it, and that patch there may be some more than two categories may be there. So center pixel, if it is not falling exactly on that thing, it may not be so accurate. So the boundaries will not come out so accurate, and occlusions and etc. Those are definite problems which are there. So another idea would be to just take, instead of running a sliding window, just give the entire input image and run it just once throughout the full network architecture, just once instead of repeatedly doing it. But now, so instead of so you modify the network in such a way that now we remove all the fully connected layers. We just have convolutional layers only. So now the fully connected layers generally which we were keeping as a classifier, instead of having those fully connected layers as a part of the classifier, have convolutional layers only as at there itself. Because when we have convolutional layers, we will preserve the inputs, the image structure, the spatial layout is preserved, and because the input is also as per image, and each layer also we preserve the basically we can preserve the weight and the width and height of the image. So you will have we will be able to preserve the height and width of the image, and in the last layer we can just ensure that we keep sufficient filters so that the channel dimension is equal to the number of class category. So if this data set we are trying to label amongst let us say 100 classes, so we will have 100 channels. So in the last layer we can have those 100 filters so that we have these 100 channels as a depth. So and each channel will represent the probability score for that pixel belonging to that particular class, and then we can take the maximum argument of all those C channels, whichever channel gives the maximum probability, that particular label will be given to that particular pixel, and in that way we'll be able to make the prediction. So that is a good idea. Theoretically, there is no problem with this idea. At least we have avoided the problem of sliding window. We don't have to recompute for same patches. We don't have to recompute the features again and again. The entire image just goes through the network just once, and all the features get computed in a single pass. So that is an advantage, but still, as there are problems with this approach. One problem is there will be too many parameters to train, because remember in the previous network architectures that we have seen for classifier, we were downsampling every time when we move to the next layer in order to reduce the parameters. So your input image may be too high resolution, maybe 720 cross 480, if it is half HD. If it is full HD, it may be 1K by 1K. But so we cannot keep that huge resolution at every level, otherwise the number of parameters becomes too much. So we keep on downsampling, subsampling, we have pooling layers which keep on reducing the parameters, and in that way we are able to manage the parameters. But here, if we preserve the height and width of the image throughout the network, we don't downsample it again, then the total number of parameters becomes too many and it will be too expensive to train all that. Another problem will be because this architecture is not same as the other previous architecture, so we cannot do transfer learning. So we'll have to train these architectures from scratch. And to train this architecture from scratch, now we'll need a very huge data set, and huge data set with all the semantic level labeling done, which is so not available. So we need a ImageNet kind of a data set which has semantic level labeling done for each pixel class has been given. So because there are too many parameters, to learn all those parameters, we need a very large data set. Otherwise, it will very quickly overfit and will not generalize. So that huge data set is also not available for semantic annotations. So this idea is also unfortunately has to be dropped. So improvement over this can be to basically don't have the entire network at the same resolution. So first of all, to avoid the problem of basically having a huge data set which has a semantic level annotation, we would like to reuse the classification networks that get trained on ImageNet, like VGGNet, GoogleNet, InceptionNet, all those things. We would like to reuse them, and we will have to adopt them as through transfer learning that we have seen earlier. Now the task is different, but we can use the features which are learned by these classifiers, so that we don't need a very huge data set. We can easily fine tune it. So only the last layers, the fully connected layers, you replace. So that is how we do transfer learning. Basically, we try to freeze the initial layers which learn the features, and the last layer, which are fully connected layers, basically you replace them. Basically, you make them into fully convolutional network, fully convolutional layers. So how do we do that? We can have 1x1 convolution layers. So this is the what is basically 1x1 convolution. So your filters will be just 1x1 filter. So let us say in the last layer we have W cross H cross D. D is the dimension depth or the channels. So your filter will be just 1x1 filter, basically. So the filter is doing no spatial aggregation. It is just 1x1 filter only. but it is just collapsing the entire channel into one. So the entire channel is just getting collapsed. This one cross one layer will help to collapse into just one. So that is how, so this entire things will get reduced to W cross H by using these one by one filters. And if you want C number of classes, we can have C number of such filters, so that the channel dimensions of this output layer becomes W cross H cross C. So that is how we use in the last layer uses C filters to get C channel dimensions representing the class probabilities. And again, we will be using the maximum out of all those C channels, which one gives the maximum probability, that will be the label for that particular pixel. But the problem with this idea is that when you are going to use classification architectures, remember the classification architectures are performing downsampling. As after every layer, they are reducing the size of the image and they are pooling and subsampling and all those. So as they go deeper, or the size of the output get reduced. So in that sense, the output, if we just, so the output then will have much lower resolution than the input. But we want the same resolution to be able to classify each pixel. So what can be done? We'll have to then perform some kind of an upsampling. So after we'll have to perform upsampling in order to get back to the original resolution. And we can do upsampling by using some traditional techniques like we have seen interpolation, bilinear interpolation, or those kinds of things, or some similar rules. But generally, it depends. The accuracy will depend on how much upsampling we have to do. So if we are doing upsampling by more than 2 or 3 or 4 times, a simple interpolation and all those things will not work basically. So we'll have to do something more. So what can be done? We'll have to use some kind of a machine learning. We need to adopt the network itself so that the network itself learns how to upsample it. So we'll see some techniques how to upsample it. I'll just recover. So there are some popular some architectures that have come out in recent last few years, which do semantic segmentation. One of the first architecture which did a quite good job was called SegNet architecture. Came out in 2017. So as we see what it is doing, it is using the normal convolutional classifier architecture like VGG net or whatever. The first part remains the same basically. And that is called encoder architecture basically, which is doing a downsampling. It is why it is called encoder. Basically, it is taking the input. It is extracting features, and it is extracting features learning. So as we go to the higher level layers, the type of features which are going to be learned by this feature layer, which is going to be more semantically close, more semantically meaningful features, because the initial level features are just edges and all those things. But higher layer features are more close to the class of that particular object. So they are more semantically meaningful features. So we are going to, so this part of the architecture is basically kind of an encoding the semantics of that image into this, and then we take that more semantically meaningful features and then upsample it to the original resolution through an upsampling network, or we call it as a decoder network or decoder architecture. And then that helps us to do the classification for pixel level classification. So the architecture is something similar. In the encoder part is same, convolution plus batch normalization plus ReLU, followed by a pooling, some sampling layer, and so on. Encoder, the decoder part has a reverse. It has, instead of a pooling layer, it has an upsampling layer which upsamples the feature output to the next level, and followed by again convolutional layers. We'll see why convolutional layers and all that things. And at the end, basically, we have this simple classifier basically. So the encoder takes the VGG16 architecture, which is one of the ImageNet image classifier architecture, which gave a high accuracy. After LXNet, this was the VGG16 one that came out. But the fully connected layers have been removed. And decoder is basically maps low resolution encoder feature. So decoder is going to take this low resolution encoder feature map, and it is going to basically upsample it to the original input resolution. And how it does it? Basically, it uses the indices so during max pooling, if you remember, during max pooling, we take a 2 by 2 or 3 by 3 window and select the maximum location and just keep that and discard the other values. So the indices, out of those 2 by 2 or 3 by 3 locations, whichever location the output was kept, those indices are preserved, and those indices information is used to basically do the upsampling. So how it is basically done? So an example is shown here. Let us say the output was this. This was an output feature map, and this was the pooling indexes from the previous layer which gave this output. So this says that this particular value came from the indices 0, 0. So let us say we were doing a max pool in 2 by 2. So let us say we were using a 2 by 2. We had done a max pooling on a 2 by 2 window. So A came from the indices 0, 0, which is the first location. Let us say this 0, 0, this 0, 1, this 1, 0, this is 0, 1, 1, and so on. So this came from 0, 0. So we will take this take 2 by 2 window and put A 0, and others were discarded. So we don't have any information about them. So we'll replace them by 0. Now B came from 1, 0 location, so B will be placed here, and C also came from 1, 0, so C will also be placed here, and D came from 0, 1, so it will be placed here. So now from 2 by 2, now we have upsampled it by to 4 by 4. But it is giving us, this is a sparse representation. Most of the values are zeros. So we'll need to make it these past upsampled maps now have to be made. We need to basically make it more meaningful map, make it more dense feature maps. Basically, not having having some non-zero values at most of these locations. To do this, we'll follow this up with a convolutional layer with simple convolution filters. So we'll have again some filters, just like we were having some filters for convolution operation. We'll have similar some filters basically here to do convolution. So those filters will get trained and those weights will get learned, and when they will perform a convolution on this, the net output will be a more dense feature map rather than this sparse feature map. And of course, for the loss function, to train this function, we use the sum of pixel-wise cross entropy loss. So cross entropy is basically a softmax function. So the total loss will be the sum of pixel-wise. So for each pixel, we'll take the loss and we'll do a summation over each pixel. So that will be basically the net optimization function, basically the loss function that will optimize. So that is your pixel-wise sum of pixel-wise cross entropy losses that we are going to minimize by training, and that will train the decoder architecture. Most of the time, the encoder architecture will be kept freezed because these weights have already been pre-trained. So you will be fine-tuning these parameters on your semantic segmentation data structure. Is that clear to everybody? Is there any doubt? Anybody has any question? Does it make sense to everybody? So let me continue forward. So there are other ways also to do this upsampling rather than this simple using pooling indices. There are other ways to do a more trainable upsampling so that we don't get a sparse output, we directly get a dense feature output. So that is called transpose convolution, which is kind of a reverse of the convolution operation. But to train the decoder portion, won't it take quite a large time? Not so large, because the number of parameters are less. We are only have to treat only half of the, and yeah, it will not be less, like few hours only. We'll have to spend some time depending on the data section of this. So it is not going to be so easy or a trivial training, but not so much that you cannot actually do it. It's not going to be a very bottleneck problem. It's not going to be a too much a problem, especially with today's things that we have. It's not so different than what we were doing in an image classifier. We were if you are able to train an image classifier, we can train this also, decoder also. So another way that to overcome that things, if you want to reduce the number of parameters and all that, so you don't instead of generating sparse output, you directly get a more dense feature output while doing the upsampling. And one way to do that upsampling is using transpose convolution instead of just using the max pool indices. This transpose convolution is kind of a reverse of a convolution operation. So when we take a convolution operation, it shrinks the size of the output from the input image. Depending on the size of the kernel, it shrinks things. And this is basically, this is going this, if you do a reverse kind of a reverse operation, which it will expand the output size. It will take, so let us say original input is just a 2x2 input, 2x2 image, and we want to make it to a 4x4 output. We can use this transpose convolution, or we can also do a striding kind of a thing, and from 2x2 we can get a 5x5 output. So try to understand how this works. It is little difficult to visualize. So there is a 1D example also I have put it here to just try to understand. A 1D example is more easy to understand. So let us say your input is maybe 4 pixel value here, which width window size is W, let's say, and let us say you are using a 1D kernel of 3. Okay, so in an transpose convolution, what we do basically, we apply this. So again, we are going to slide this kernel along the input size. So we start from this location, and we basically do a convolution operation. So here, so 2 into 1, we get 2, 2 into 2, 4, 2 into 1, minus 1, minus 2. So we get one output here. Then we shift. So when we get this output here, so this the first output is already ready here, because no other input pixels are going to make a contribution to it. So this first output is already ready here. So here also you can see the first pixel of this expanded output is already has come from this particular pixel multiplied by this particular weight of the filter. And similarly here. But for the next output, we will have to shift the filter by 1. And then for this particular, we convolve with this input value with all these filter values. So we get these values. And we are going to sum these two. So this particular output will be obtained by adding these two. 3 into 4 going to give 7. Similarly here, probably these two locations are going to contribute to this, and so on. And here is basically a stride kind of a thing is given, or gap is given basically. So we continue this, shifting this thing over things and calculate the response. And the final response, basically we take the individual contributions. So if you can visualize it, I don't know whether you're able to visualize, it's just kind of a reverse. In the original convolution operation, we were taking the input image and we are taking the filter, and we were getting basically a sum of weighted input. And we are replacing the center pixel by a sum of weighted input. Here we are doing the reverse basically. So we are taking the each pixel, and we are basically calculating the output response by where each pixel is contributing each pixel is contributing by these weights of the filter towards the aggregate output value. So it's little difficult to visualize, but I hope later on you can try to understand it. But it's almost a reverse dynamics, so of the normal convolution operation. So that's why it's called, some places it's called deconvolution, but that is not a that term is already used for some other context in signal processing. So people in machine learning domain, they started calling it as transpose convolution. So it is going to basically generate now. So now you will not be having zero values all over place. We will having non-zero values at all the locations. So we all will be getting a dense feature map automatically. So we don't have to do that many convolutions and after this. So this will reduce the number, the decoding weight, the number of weights that are required. Of course, these weights have to be learned. These filters weights have to be learned, and these weights will get learned just like through back propagation, just like the encoder filters get learned. Similarly, these filter weights will also get learned by the back propagation strategy. So some of the improved architecture using all these things. One after SegNet, the one which came was kind of a UNet. It's almost similar to SegNet, which has a encoder and then a decoder phase. So this is basically encoder and then this is a decoder phase. But along with that, it has skip connections. So you have an encoder stage, take input, generate features, subsample it, generates features. But now instead of only taking the semantically meaningful features at the last, at the output of the encoder and then just upsampling that, we also concatenate the features learned from the corresponding encoder level layer. So we take this, so when we are upsampling an image from this to this resolution, so we take the features that were learned at this stage, concatenate it with the, apart from the upsampling, we also do a concatenation. So that is what is being shown here. So concatenation can be either simply summing up the values from here and the values from here, or some way of concatenation. But the idea with this concatenation is that it is found to give better localization information to the decoder. So instead of just upsampling, when we are using these features which have been learned at that particular scale in the decoder during the encoding phase, we use those features also and then it gives a better localization information. So while segmenting out, your boundaries are more accurate rather than having. So when you just upsample it, remember the problem of upsampling. When we do simple interpolation, you may end up getting a coarse estimation of the boundary. So, but by doing these things, people found that the it gave a more accurate boundary segmentation results. So because you are preserving now, we are utilizing these features that have been learned at each scale, which gives a better localization information. Okay, so and then there are some more basically modification that came. I'm not going to go into more detail of this. This is also similar, but it is called spatial pyramid pooling. Here, apart from doing all those things that we have seen, they also do another thing called spatial pyramid pooling, which is nothing but we have already seen that so the features that have been learned by the encoder, instead of keeping it at one particular scale, they produce that features at multiple scales. So you get a scale space. So that is what pyramid is basically meant for. We have seen this pyramid thing earlier. So generating these features at different scales. So because the problem, people found that for very complex scenes where we have large objects combined with small objects, or some things which go together, like a car always goes with a road, or maybe a boat always goes along with a water body and so on. So those co-adaptation or co-learning and all those things, and handling more complex patterns or things, learning all those things is not becomes difficult until unless we preserve the global context along with the local context. So we preserve the context at different scales. So when we use the information at different scales and use all that for the segmentation purpose, then we perform even in complex scenes, the results are better. So I'm not going to go into more details, but I hope you get some idea, some intuition behind it. So it is going to do that thing, and either you do simple upsampling, or again you do skip connections, take concatenation from the feature map. And this part is trained on ImageNet. we pre-train on ImageNet and just you fine-tune the decoder stage. So these are some sample results using these some of the later architectures of these segmentation. You can see quite remarkable results are there. These are some input scenes and the output semantic level prediction, basically colored by as per their class label. So you can see, for example, this not only the classifier is able to predict this segment out this bird, but it's also able to do a segmentation at very fine level. These small claws or whatever you say is feeds are basically also getting learned that these are part of this large object. So they are not being treated as a separate object. They are being basically treated as one object, basically. Here, of course, what they have done is they have also kept one background class. So because in the data set they may not be able to generate labels for all possible categories in these classes. So they may have fixed this for 20 classes or so, and all other rest they have counted it as a background class. So the black is basically showing as a background class. So if it is not one of the meaningful classes, then it is being shown as a background class, and background class is treated as a separate class. And you can see basically you can see the outputs are quite good. So even this body, although she is basically sticking out her feet outside, but still the classifier has learned that this portion is also the part of the same person. Although the normal person's pose will not be this, but still it has done this, been able to learn this somehow that this is part of the same person here. And these are another good results. Some of them are not so good. I think, for example, here probably it's not able to properly segment out this horse which is behind this bars properly. So some of them which because of the lack of the information or complex or maybe a more complex scene like this, you can where there are too many digits, the results may not be so much satisfying, but still it's good enough results which cannot be possible by traditional techniques, maybe techniques that we have seen, k-means or mean shift and all those things. These fine level segmentations may not come out as good because of the different patterns. Even within the same class, probably you can see the variations are too many, and to do that is not easy. All these various challenges cannot be handled by traditional heuristic based techniques, but these deep learning based techniques tend to learn that because of the huge samples that are available and a good amount of training that is done. So how much time is left? Okay, so let me cover the second task now. So we have discussed semantic segmentation to sufficient detail now. Second task is much more easy. It's we have to just do a slight modification. So now we want to we have seen how to do how to solve this task of classification, but along with that we want to now add this functionality of doing a localization. So not only just give a label, but also draw a bounding box for that particular object in the class. So how we can do that? So for generating label, we have seen we have this CNN architecture, and at the last we have a fully connected layer, which basically has the number of classes. So if you have 1,000 classes in an ImageNet data set, so the last layer will have 1,000 neurons, which will be fully connected, and it will give the class score, and that will do a classification task. Now to get the localization task, we need a bounding box basically around this. So we need a bounding box around this particular object. So we need to predict this location of this bounding box. So we need to predict, for example, the xy, the center of this bounding box, xy coordinate, and the width and the height of this bounding box. So we need at least these four values to be predicted. So how we can do that? So the simplest or straightforward modification of this architecture will be this last layer will have not two heads. So so this architecture will have two heads. One head just does the normal classification. The other head is kind of a regression head, which now basically will be connected to four neurons, which will be predicting these outputs. And these will be a regression neurons instead of a classifier. These will be a regression task because now we need a real valued response output here. So we'll treat this localization problem as a regression problem. We'll cast it as a regression problem. And the loss function for this will be L2 loss, which is basically a Euclidean distance loss, or we can take an L1 loss, which is simply a absolute difference loss. So we have a correct in the ground truth. We'll have a correct bounding box label values, and our network will predict some values, and we'll take from the correct ground truth. We'll find the L2 loss, and for the classification we use the softmax loss. So we'll add these two losses. So now we'll have a multi-loss optimization function. So we'll do some kind of weighting also, maybe some weight to the softmax loss and some weight to the L2 loss. So and that weighted loss will be the final loss. And this final loss will be optimized during the training phase. So weights will get learned during the backpropagation. Of course, as we said, this part of the network we don't need to retrain. Most of the training will be done for this part, which can be done on a reasonably small size data set also. So is that clear? Does that make sense to everybody? Any question? Okay, so if that is okay, then let us move to the next part, object detection. So we'll introduce how the problem of object detection and how we approach it, but we'll discuss the exact architectures in the next class. So coming to the object detection task, first of all, we need a different data set for object detection task. So in object detection task, we need a data set where the bounding box for each object that we want to detect have been labeled, and their locations and height, width, and all those things have been annotated. So one of the first large detection data set that came out was Pascal dataset, which is also called sometimes simply VOC dataset. And along with ImageNet, I think there was challenge for this Pascal dataset also detection. It was mainly meant for detection, but it also had semantic level annotation. So it was also used for semantic segmentation. So for the previous semantic segmentation tasks, normally people would use this Pascal dataset only for learning the overall architecture, fine-tuning the parameters of the decoder or the final classifier. Okay, but this is also mainly used for the object detection. We have 20 classes in this. In total, we have some 11,500 training images. And in those 11,500, the total number of objects that are annotated are around 27,000. So in some image has just one or two images, two objects. Some images have multiple objects, maybe occluded also, or very close together, and so on. So how do we basically judge the goodness of a particular object detector? So earlier we were using simple and accuracy metric for seeing how an architecture or network is performing well. But now for detection, we need another metric, and the usual metric that is taken is basically an IOU called intersection over union metric. So what is this intersection over union metric? So let us say you have a ground truth which is marked, let us say, by B2, and your detected output is marked by B1. So how good this is matching with the ground truth bounding box? So you first find intersection of these two bounding box, and then find the union of these two bounding box and take the ratio. So the ratio will be the intersection area divided by the union area. So a large value of IOU means a good detection. A small value of IOU means bad detection, basically. So if this detection does not overlap with the actual ground truth, then intersection will be minimal or zero, and union will be very high value. So it will make a value close to zero. Similarly, if it is almost exactly fitting the ground truth, intersection will be same as the actual thing, and union will also be same. So it will almost become 1. So 1 is the perfect match, and 0 or close to 0 will be low score. Sorry, I had this animation also. So let us say we want to find out this detection, how we, so let us say this is the ground truth of this particular object in this image. And if we run our detector, and probably detector finds these different yellow boxes for this particular object. So which of these three boxes is a good detection? How do we know? We will calculate IOU. So for this particular box, this is the intersection value, and this is the union value. So an IOU score will not be that good. It will be somewhere around 2.5 or less than 0.5. So if you take the basically this bounding box, again intersection over union will be a low score. But if you take this bounding box, this will have the highest IOU value. So out of those three bounding box, this will be the closest bounding box because it is most closely matching with the ground truth. So that will be chosen. So that is how we decide the correct bounding box. We take the intersection over union, and we generally keep a threshold. So maybe around 0.5 or 0.7 or whatever. So anything less than that, we don't consider it as a correct bounding box. We have to take it beyond that. And of course, now, so the metric that we will be using to basically judge the goodness of that object detector. So now there will be two metrics: recall and precision. Recall is basically, if you remember, so let us say there were three ground truth objects in the scene, and let us say your classifier detected these three, or your classifier detected these two, plus it detected some false. So it has two true positive and one false positive, and it has missed one actual object there. So in this case, the recall will be the correct bounding box, which is 2 upon the total were 3. So 2 by 3 will be the recall, and precision will be 2 out of, it has totally detected 3, but out of 3 there are only 2 correct, so 2 out of 3 here. So precision will be calculated that way, and recall will be calculated that way. So now it depends on what threshold value you consider as the correct bounding box. If you keep this threshold value very high, let us say keep it close to 0.9 or things, then you will be only getting most confident prediction. In that case, you will have a high precision, but your recall will get low. You will miss many of the objects which are there in the image. So generally, what happens when you keep a high threshold, your precision increases, but your recall goes down. And whereas vice versa, if you lower your threshold, your precision will become less, but you will get high recall. You will be able to detect most of the objects which are there in the scene. So what generally done, we need some kind of an average criteria over it. So we can vary threshold. One way is we vary threshold and plot this precision recall. So if we keep threshold high, then precision will be high and recall will be low. And if we reduce the threshold, then recall will increase and precision will go low. So we'll get this kind of a precision recall curve. Okay, so now the average precision, so these are different curves for different classes, let us say. So for each class of objects, we'll calculate this precision curve, precision recall curve. And then average precision for a particular class will be basically the area under this PR curve for that particular class. So for each recall, what is the precision we got, and if we take an average, that average is basically an area under this curve, and that is for single class. And if you want to consider all classes, so we can take mean of that average precision across all classes. So across all these curves, we calculate the area and then take an average. So that gives a mean average precision. So that is the final metric that we use for judging the goodness of our object detector. That is called mean average precision, which is basically mean of average precision across each classes. And this may also be sometimes fixed for a particular threshold value, a threshold of particular IOU value, which we consider it from where we start considering whether the bounding boss detector or bounding boss is correct or not. So we can keep it at 0.5 or 0.75. So most of these data set, when they give out challenges, they will say that you have to report your mean average precision at IOU value of 0.5, and then people compete over that. So this challenge had been there over the years, and as you see, before 2012, you were having basically traditional techniques which were performing far less. They were having only mean precision score up to 40%, or maybe near around 50%. So this was probably the last one was this Dalal and Triggs SVM, HOG, SVM, using SVM and HOG to detect persons and pedestrians. But from after this AlexNet and after this image classifier, then people started using those deep learning architectures for object detector also. And then over successive years, we can see the mean precision, the mean average precision has considerably increased. So this earlier it was got saturated and it was not increasing. But again, with the introduction of deep learning, it has not only increased, but it has come to a nearby human level performance. Not maybe exactly human level, but at least acceptable level around 80-85%. And this around 2015, I think 16. So in this slide does not have more recent things. More recent versions have a very high accuracy, that it has become possible to use to commercially deploy these techniques in commercial products. So I think we are up with time. So we'll discuss the how to solve this problem in the next class probably. So we'll stop here.